All right, so 748 is just getting into the idea of how are sine and cosine related. So it says, if you know the sine of an angle on the unit circle, can you find its cosine? How? And then to work with your team to come up with a strategy. So what they're trying to get at is the fact that we're talking about a right triangle. So if I know it's a right triangle and it's the unit circle, meaning the radius of the circle is 1 unit, that would mean each hypotenuse has to be 1 unit. And if I know the sine, meaning I know this side, I can use Pythagorean theorem, which is what they're trying to lead you to right now. So let's say, for example, that I know that the sine of this particular triangle is 1/2. In order for me to find this missing side down here, I could just go x squared plus 0.5 squared equals 1 squared. So x squared equals, this would be 1/2 squared, which is 1/4. 1 squared is 1, so this would be 3/4 when I subtract it over. And then I can square root both sides. Now, this is probably one of my favorite things about square roots, is you can actually break it into pieces. So since I'm taking the square root of a fraction, I can actually take the square root of the numerator and the denominator separately. So the square root of 3 divided by the square root of 4, which you'll see me write a lot of the time as square root of 3 over 2. So since I know that the sine of my triangle is 0.5, I'm able to find the cosine of my triangle, or the width of my triangle. And this is an idea that should be super familiar to us. So we've been talking about Pythagorean theorem for forever, since like Algebra 1, I think. And they're just leading you into this idea because it's something called the Pythagorean identity. So in 49, they bring this up. It says an angle theta on the unit circle has a cosine of 3/4. Find the exact coordinates of point Q by using the Pythagorean theorem. So there's kind of two different ways we can go about this. The way that kind of comes into my mind is setting up my own triangle off to the side. So it says an angle theta on the unit circle is 3/4. So in my brain, the way that I think about this is, since I know it's cosine, that tells me that the adjacent side over the hypotenuse has to work out to 3/4. So if it's adjacent over hypotenuse, that lends itself really nicely to the adjacent side being 3 and the hypotenuse being 4. And then from here, I would be able to find this missing side by using Pythagorean theorem. So 3 squared plus y squared equals 4 squared. So 9 plus y squared equals 16. Y squared equals 7. Or y is the square root of 7. However, they were specific and they said they wanted the unit circle, which means they only want that hypotenuse to be 1. But now that I've found this, I can actually just scale it down using like what we learned about for similar triangles. So since I know the hypotenuse was originally 4 and I want a hypotenuse of 1, I could just divide each of my measurements by 4. And now I've got what I need. So that's one way to go about this. A separate way to go about this is to actually just set this up kind of the way that we've been talking about all along. So we're saying cosine is going to give us the bottom side of our triangle. So if it's a unit circle, I know that's one, or a unit triangle, I know that's 1. And since we're saying cosine has to be 3/4, I could just say this bottom side is going to be 3/4, which you'll notice in my original example up here, that's exactly what I got. And then I can use Pythagorean theorem to find that missing side. So 3/4 squared plus y squared equals 1 squared. 3/4 would be 9 over 16, because just like I can take the square root of pieces, I can square pieces separately. Plus y squared equals 1. Subtract that over to the other side, and I get y squared equals 7 over 16. Take the square root of both sides. That would give me y equals the square root of 7 over 16. And just like up above, where I said I can take the square root of the pieces individually, I get the square root of 7 over the square root of 16, which is the square root of 7 over 4, which is exactly what I got up here. So this whole idea is the Pythagorean identity, which is just saying that whatever your sine value is squared plus whatever your cosine value is squared is going to work out to be 1. So that is going to be one of those things that comes up a lot. In fact, if you have a friend who's in pre-calc right now, they're probably talking about the Pythagorean identity on a regular basis. So this is something we're going to use a ton of time. Now, when you move on to 50, it's asking you to get the green piece of paper that the sub should have. It looks like this. Now, one side says 714 on the top, and one side says 712 on the top. I want you to be on the 714 side, because this is going to be our cosine side. Now, they've drawn in 5 triangles for you at those same 15-degree increments that we talked about last class. Now, we want to find the length of each of the bases of these triangles inside the unit circle. So I want to find this length, then this length, then that one, then that one, then that one. Now, I made a really big table, just like we did the other day, on the top of my paper. So I'm going in 15-degree increments all along the top. Okay. So it says, label the length of the base of each triangle on the unit circle. Plot these lengths at their angle location on the coordinate system to the right of the circle. You'll be plotting the forms in the form x equals angle in degrees and y equals that base length. Now, if my angle is originally 0 degrees, that would mean that my original length would be 1. So at 0 degrees, I'm going to start at 1. And then I'm going to get out my calculator and start to find these missing lengths. So in my calculator, if I type in cosine of 15 degrees, I get 0.96. If I do cosine of 30 degrees, you're going to get like 0.707, which conveniently is exactly what I had over here, square root of 3 over 2. Then I'm going to do cosine of 45 degrees. Oh, I might have these backwards. Let's find out. Cosine of 45 degrees. Oh, I do. 707 should be here. At 45 degrees. At 30 degrees, it should be cosine of 30. 0.866. Then at 60 degrees, I'll get 0.5. At 70 degrees, or 75 degrees, I'll get 0.26. And at 90 degrees, I'll get 0. Now, all I'm doing is typing these into my calculator. Now, unfortunately, I only have my phone with me, but I would go like cosine of 45 degrees and hit enter. So that's how I'm getting those. Now it asks us to plot each of them. So 0.96, 0.86, 0.707, 0.5, 0.26, and 0. Then it says draw 5 new triangles that are the congruent to the first 5 but are located in the second quadrant. So they're asking us to make the 5 triangles over here that would match with these. Hopefully what you're noticing is this is exactly like what we talked about with sine, that there's going to be some symmetry going on that we can use. So I've got my 5 new triangles. This would be at 105, 120, 135, 150, 165, and then 180. Now, I'm not going to go through and type those all in. You absolutely could if you would like to, but what you're going to see is exactly what we saw last time, that these are going to match what we had over here. The only difference is that now, since we're talking cosine, we're talking x values, so side to side, meaning that everything on this side of the y-axis is going to be negative. Everything on this side is going to be positive. So all the numbers we just found are positive, but these are going to be the matching negative versions. So at 105, I would actually be at negative 0.26. At 120, I'd be at negative 0.5. negative 0.707, negative 0.86, negative 0.96, and negative 1. So I end up with a graph. That's a little far. Should be like there. So now it looks, I'm tilted kind of funny. There we go. Kind of like this. Part C says to continue this process, so to go into the next 2 quadrants and do the exact same thing. So you would fill out the rest of your table. Let's see. Six. And hopefully you're starting to get kind of that spidey sense going on where you're recognizing these numbers, where they feel very familiar to us from previous classes. So what you're going to see is that these are the exact same numbers as what we had when we were talking about the sine graph, except now they are on a slightly different place on our graph. So let me just finish my graph off here. And then I can compare. So if I look at these, the cosine numbers end up starting at 1, going to 0, negative 1, 0, positive 1, where sine started at 0 and then went up, back to 0, negative 1, back to 0. But the numbers are all exactly the same. So hopefully that looks really, really familiar to you. And that's the entire idea that we talked about last class.